Say about himself, he's a lead engineer on Twitter's publisher analytics team. Previously, Nathan was the lead engineer of Backtype, which was acquired by Twitter in July of 2011. He is a major believer in the power of open source and has authored some significant open source projects, including Cascalog, ElephantDB, and Storm. And he writes a blog, which you can find at nathanmarks.com.
Can you guys hear me? No? You guys hear me now? All right, good. All right, well, let's get started. So this talk's a little bit different than the other talks, because it's not about Hadoop. It's about a different system, but Storm fills a really big hole in the big data processing space. So I'm looking forward to talking about it. Just some basic information about the project. Storm was open sourced on September 19th. The implementation has only 12,000 lines of code. About half of that is Java and half of that is Clojure. Storm, even though it hasn't really been around that long, it's already used by over 25 companies. It's the most watched project, or the most watched JVM project on GitHub, and it has a very active mailing list and a very active community. So you guys are all familiar with Hadoop. Hadoop is a batch computation system that's distributed and fault-tolerant. Storm is a real-time computation system that is also distributed and fault-tolerant. With Hadoop, you run large, finite jobs. You process a lot of data at once. And Hadoop jobs are, because of the nature of the processing, are inherently high latency. Storm is different. With Storm, you run infinite computations called topologies. With Storm, you process infinite streams of data. Computational model of Storm is processing one tuple at a time, and Storm is low latency processing, real-time processing. So before we get into Storm, I just want to say a few words on how we built systems before Storm, and what were the problems associated with that. Now, what we did before Storm is we built our real-time components using the queues and workers paradigm. Very common paradigm used by lots and lots of people. So our architecture used to look something like this. It's a little bit of a simplified version of what we used to have. But we were processing the Twitter fire hose. We put the Twitter fire hose onto a set of queue servers. And then we had a set of workers that would take the tweets and schemify them and append them to Hadoop. And then they would extract URLs from the tweets and pass them off to another set of workers through another set of intermediary queues. And that second set of workers would update statistics on those URLs by incrementing various counters in Cassandra. So there were a lot of problems with this approach, and here's just a few of them. First of all, scaling a system like this is very, very painful. Let's say you wanted to scale those workers that write to Cassandra. We'd have to deploy a new worker, get it running, possibly deploy a new queue for it. And if the workers that are passing messages to those workers are doing things like hash partitioning, then you need to update that set of workers as well to know that the consuming workers now have a different number of workers. The fault tolerance of the system is also very poor. There's things you can do to add failover by having failover workers and things like that, but it's all very brittle at the end. And finally, coding these things is very tedious. You spend most of your time worrying about where are you going to send messages to, where do you read messages from, how are you going to serialize messages. When you actually get down to the logic you care about, it corresponds to a relatively small percentage of your code base. So we looked at this system we had and a variety of other real-time computation problems, and we came up with this list of things that we need from a good real-time computation system. So the first is that a real-time computation system must guarantee data processing. There's just too many problems that require this. The second is it must be horizontally scalable, and not just that, but easily horizontally scalable. So add a node, tweak a few knobs, and have it just work. The third is that it must be fully fault tolerant. So that means if a node goes down or there's some error during the processing, it will self-heal and keep on going. The fourth property here is interesting. Here I say we want to get rid of all those intermediate message brokers. Now, you have to ask yourself, why do those intermediate message brokers exist in the first place? Well, the reason is actually for that guaranteeing data processing property that we want. So like here, if one of the Cassandra workers fails to process a message, well, then they can just replay that message off of that intermediary queue. If we get rid of all those intermediary queues, then we need a new strategy for guaranteeing message processing. Fifth, we want a higher level abstraction of message processing. So as I said, that paradigm is very low level and tedious, and we want to work at a higher level of abstraction and focus on our real-time logic. The sixth property is that a real-time computation system must be extraordinarily robust. So let me use Hadoop as a point of comparison. I'm sure everyone here has encountered a situation where Hadoop has been down for a few hours. Because you hit some issue and you have some weird stack trace in the logs, and it takes you a while to figure out what's that configuration parameter you need to tune to get it back up and running. But in some ways, that's okay for Hadoop. Hadoop is a high latency system, so if you take a few hours of downtime, well, you're still high latency. Now with a real-time system, if you take a few hours of downtime, you're no longer real-time. So the robustness requirements are much, much, much higher. Right, and of course, Storm does satisfy all these properties. So there's three broad sets of use cases for Storm. These are by no means all-inclusive. The first one I call stream processing. So the idea here is that you process some stream of messages, like a stream of tweets, and then you update various databases based on those messages. The second use case I call distributed RPC, and I'll be talking more about this later in the talk. The idea here is that you have some function that you want to compute on the fly, something that's really intense to compute, too hard to compute for a single machine. We can actually implement that function as a Storm topology and use Storm to parallelize the computation and use it as an RPC mechanism. The third use case I call continuous computation. The idea here is that you have some function where you want to continuously know the results to it. So an example of this is computing something like trending topics off of the Twitter fire hose. So a Storm cluster looks like this. There's three pieces to it. On the left we have Nimbus. Nimbus is the master node and plays a role similar to the Hadoop job tracker. When you have a topology you want to submit, you give Nimbus the jar containing all your code as well as the structure defining your topology. And Nimbus will take care of distributing the code around the cluster and launching the workers to run the topology. And then Nimbus will also monitor the computation and restart any workers and other machines if they fail. In the middle we have a Zookeeper cluster. So this is used to coordinate the cluster. This is pretty much exactly what Zookeeper was built for. And finally, we have a set of worker nodes on the right. Every worker node runs a daemon called the supervisor. And the supervisor communicates with Nimbus through Zookeeper to determine what should be running on that machine. And then it will just start and stop processes as necessary. So let's say you have some computation you want to run. Well, here's how you would start it on a Storm cluster. As you can see, it looks very similar to how you run jobs on Hadoop. So there's a command line client called Storm. And you say storm jar, give it the jar containing the code, and then you tell it the name of the class and the arguments to the class, and this will go ahead and upload the jar and submit the topology to Nimbus. If you have topologies run forever, but if you ever want to kill a topology, you say storm kill and then the name of the topology. All right, so let's dig into the abstractions of the Storm. So there's four main abstractions: streams, spouts, bolts, and topologies. A stream is an infinite sequence of tuples. And a tuple is just a named list of values. When you're using Storm, Storm is all about taking big streams of data and transforming them and manipulating them. The second abstraction is called a spout. And a spout is a source of streams in a computation. So for example, you may have a spout that reads a stream from a Kestrel queue and emits that into the topology. Or you may have a spout which connects directly to the Twitter streaming API and emits those tweets as a stream into the topology. The next abstraction is called a bolt. And a bolt takes in any number of input streams and produces any number of output streams. When you're using Storm, most of your logic goes into these bolts. So bolts do everything from run functions, do filtering, do streaming aggregations, do streaming joins, talk to databases, and so on. All right, and finally, the top level abstraction is called a topology. The topology is simply a network of spouts and bolts, where every edge in the graph indicates a bolt subscribing to an output stream of some other spout or bolt. So the key thing about Storm is that spouts and bolts are inherently parallel. They execute as many tasks across the cluster. Right, so here you can see the spout on the left has 2 tasks, the bolt on the top has 3 tasks, and you can see that the tasks actually pass messages directly to one another. So this is the logical view in that every abstraction in topology has some number of tasks. When it actually executes, the tasks are spread out across the cluster. So here, every big box in this diagram is like a worker node, and here you can see like the tasks for spout S. We have one on the top node, one on the left node, and you can see the tasks for the bolts and spouts are spread and mixed all across the cluster. And then these workers communicate with each other using message passing. All right, so bolts and spouts are parallel. They execute as many tasks. Well, this brings up the question of when a task commits a tuple to some consuming bolt, to which task does it send the tuple to? And you answer this question in Storm by providing what's called a stream grouping. So the simplest kind of grouping is called a shuffle grouping. And a shuffle grouping simply tells it, just pick a random task to send this message to. And this has the effect of evenly distributing the load of processing that stream. A more interesting kind of grouping is called a fields grouping. So here it actually takes the hash mod of a subset of the tuple fields to choose the target task. So this is very similar to like how Hadoop's grouping mechanism was. Another kind of grouping is called an all grouping. So in this case, it actually replicates the tuple across all tasks. This is obviously something that you should use with care. A global grouping sends all the tuples to a single task by picking the task with the lowest ID. And there's a few other kinds of groupings, but those are beyond the scope of this talk. So if we actually look at a topology, it looks more like this, where we just annotate the graph with the kind of stream grouping used for every subscription. All right, so I've done a lot of talking, so let's look at the actual code for using Storm. So kind of like how Hadoop's canonical example is word count, here I'm going to show you how to do streaming word count on top of Storm. So the first thing you do is you create this topology builder object. The topology builder exposes a very nice API for constructing topologies with Java. So the first thing we do is we will set our spout in the topology. So here we say, let's create a spout, and we'll give it an ID of spout. And then the implementation is a kestrel spout, which reads off the sentence queue from that host and port. And then we'll give this spout a parallelism of 5. So this will execute as 5 tasks across the cluster, and each task will be hitting that kestrel node to get messages. All right, now let's create our first bolt. So this bolt, we'll call it split. We'll give it the ID of split. The implementation of this bolt is in the split sentence object. So this bolt will take in a stream of sentences and emit a stream of words. We give this bolt a parallelism of 8, and we'd say that this bolt reads its input from the spout component, which is what we defined over here, and it uses a shuffle grouping on that stream. All right, so you can see that it's the consumer that decides what data it receives and how it gets grouped. All right, and finally the last bolt is the word count bolt. We give it an ID of count. The implementation is the word count object. We give it a parallelism of 12. And then we say this bolt reads the output of the split component using a fields grouping on the words field. So this has the effect of the same word will always go to the same task, but different words may go to different tasks. Now the reason we use a fields grouping here rather than shuffle grouping is because if we use a shuffle grouping, the same word can go to multiple tasks, and each task will have an incomplete view of how many times that word is repeated. If you use a fields grouping, the same word always goes to the same task, and then that can emit the correct count for that word. So here's the implementation of split sentence. So here it's actually implemented in Python just to show off Storm's multi-language capabilities. So At the top is a small wrapper class, which just says, I'm implemented in Python. And at the bottom, you can see whenever it's given a new tuple to process, it takes the first field of the tuple, splits it on white space, and then emits a new one tuple for every word. Here's the word count vault. So this is implemented in Java. So the way this works is it keeps a in-memory hash map from words to counts. You could use a database instead of just doing it in memory here for simplicity. And then when it receives a new tuple in the execute method, it updates the in-memory map and then emits the updated word count. And that's it. So if you wanted to submit this onto a cluster, you would do this. So first you create what's called a topology configuration. So this is kind of similar to the Hadoop job con. And this is just used to tweak various aspects of how topologies execute. So here we say, let's run this topology with 10 workers. So that just means there will be 10 physical JVMs running this topology across the cluster, and every physical JVM will execute some subset of the total tasks for the topology. Then to submit it, you say storm submitter, submit topology, you give the topology a name, give it a configuration, and then you give it the topology. Storm also has a local mode where you can simulate a storm cluster in process and run topologies on it. This is very useful for development and testing. So you submit in local mode, just like how you submit in remote mode. We're very similar. Here it sets the topology debug configuration. This has the effect of logging to console every time a message is emitted. This is very useful for debugging. All right, so let me show this actually running so you can see what it looks like. So here's the word count topology. It's pretty much what I just showed you. The only difference is that I replaced the Kestrel spout with in-memory spout, which submits random sentences. So let me run it. Okay, so it's running. I have it set to run for 10 seconds and then shut down. So let me let it finish. All right, so it finished. So let me just show you what happened. All right, so here the sentence, Snow White and the Seven Dwarfs was emitted. And then you can see the split sentence vault picks it up and it starts to emit snow. And then before it even has a chance to emit white, the word count vault picks it up and emits the updated count for snow. And then you can see all the computation is interleaved because it's all running in parallel. All right, so that's the basics of Storm. So now I want to talk a little bit about distributed RPC. So distributed RPC is it's not so much a feature of Storm as it is a pattern built on top of Storm's primitives of streams, spouts, fault, and topologies. So it's a little bit of a higher level abstraction on Storm. So just to recap what I said in the beginning, the idea of distributed RPC is that you have some really intense function that you want to parallelize on the fly. And you can use a Storm cluster for that. So here's how the data flow works for distributed RPC. So I'll just refer to it as DRPC. So let's say you're on the left and you have some function that you want to execute. So what you do is you tell the DRPC server, here's the function I want to execute, and here are the arguments for that request. So the Storm comes with an implementation of the DRPC server, and it just serves the role of managing the coordination of a blocking RPC request into an asynchronous topology. So the DRPC server will block on the client's request, and then the DRPC server is actually a spout. So the topology implementing the function will read the function invocation as a stream. So that function invocation stream contains the request ID, the arguments to the request, which is provided by the client, and then the return info, which is just the host port of the DRPC server. So the spout picks that up, emits it into the topology. Your topology does its thing to compute the function, and at the end, your topology gives the request ID and the result to a special bolt at the end. And then that bolt connects to the DRPC server, tells it, okay, here's the result for this request ID. The DRPC server maps that result to the waiting client and sends it the result. So from the client's perspective, it looks just like normal RPC, but it's actually executing asynchronously and in parallel in the background. So let me give an example of what you might use DRPC for. So So this example is computing the reach of a URL on Twitter on the fly. So the reach of a URL is the number of unique people exposed to a URL on Twitter. To compute reach, you have to take the URL, then you have to get all the people who ever tweeted that URL. Then for each of those people, you have to get all of their followers, and then you have to take that potentially huge set of followers and distinct it, and then count the distinct set to get your reach. So for something like a TechCrunch URL, this can involve thousands of database calls and tens of millions of follower records. Now, we originally had an implementation of this that just ran on a single machine, and for hard URLs, it could literally take minutes to run. When we did it on a 10-node storm cluster, we got that down to 2 seconds. And the topology for reach is really simple and actually really elegant. Here's what it looks like. So you have your spout that emits the DRPC function indications. So that emits a stream containing request ID and URL. The first bolt is called getTweeters, and that. Sorry. David Dynamite is calling.
A little comic, really.
So that first bolt called getTweeters maps a stream of request ID URL to a stream of request ID tweeter ID. Right? So a single URL tuple gets mapped to some number of tweeter tuples. Then getFollowers maps a stream of request ID tweeter ID to a stream of request ID follower ID. Right? So at this point now you have some massive set of tuples for that request. The next bolt is called partial distinct. So what partial distinct does is does a fields grouping on that stream by the follower ID. So this means the same follower ID will always go to the same task. What partial distinct does is collects all, the set of all the followers for that request that it sees, and then it emits the unique count of that set. And the trick here is that because it does the fields grouping, the set of followers each task receives is mutually independent from all the other tasks. So once they emit their partial counts, all that's left to finish the computation is do a global grouping and sum the counts together to finish the reach computation. And here's how it maps to code. It's pretty much exactly what I just described. So like I was saying, DRPC is a higher level abstraction on Storm. So instead of using the normal topology builder, there's a linear DRPC topology builder. And so we create the builder, you add a bolt, which is getTweeters, add a bolt called getFollowers, which does a shuffle grouping, add the partial unique bolt, which does a fields grouping on the ID and follower, and then add the count aggregator bolt, which does a fields grouping on ID, which is the same as a global grouping for that ID. So getTweeters and getFollowers are very straightforward. I do want to show how partial unique works. So one of the things the linear DRPC topology builder provides you is this, you see in the top right, that finished callback interface. If you implement that, then it will give you a callback when you've received all the tuples for a particular request ID. So the way partial unique works is that we keep an in-memory map from request ID to the set of followers we've seen so far for that request. So in execute, we just add that follower to the set for that request ID. And then when we get the finished ID callback, we just emit the partial count for that request ID. Right? And count aggregator does a very similar thing. So let me actually show this in action. So here's the reach topology. I'm not going to be querying actual databases. I'll just be mocking out the tweeters DB and the followers DB with these in-memory hash maps. But let me actually run it. All right, so what I have open here is a closure REPL. So I'm just going to use this to execute Java code, to execute it interactively. So first thing I'm going to do is create a local DRPC server. So just like regular Storm clusters, you can simulate all the DRPC locally. Now I'm going to create my local Storm cluster. Okay. And you can see it started up, and now it's waiting because it's not running anything. So now I'm going to create and submit the reach topology for execution. Right? So now it's launching the topology, and you can see the topology is not doing anything because there's no function indications. Okay, and now I can just execute some methods on the DRPC server. So here I said execute the reach function with this URL. And the reach for that was, you can see, it came back with 14. Right? If I give it a different URL, I get a different result. And then if I give it a URL it's never seen before, I get 0, just like you'd expect. All right. So the next thing I want to talk about is how Storm guarantees data processing. So I said in the beginning that we're going to get rid of all those intermediate message brokers because they're really complex and slow. So if we get rid of those, how does Storm guarantee data processing? What happens if a node dies in the middle of the computation and you lose all those messages? So first thing we'll do is let's just define what does it even mean to process a message. So the idea is that let's look at what happens to a tuple when it comes off the spout. Right? So let's take the word count example, or let's take word count as an example. So we have some sentence that comes off the spout. We'll call that the spout tuple. It's the cow jumped over the moon. Well, that tuple goes to the split sentence vault, which then emits a bunch of tuples based on that tuple. Right? So it emits all the words for that sentence. Right? And we can just diagram which tuples was every tuple based on. Right? And you end up with this tree of messages. So the tuples that vault emits goes to another tuple, which emits more messages, and so on and so on. You potentially have a very, very, very large tuple tree, all triggered by that one original spout tuple. So Storm says that we don't consider a spout tuple to be fully processed until the whole tree has been exhausted and every individual tuple in that tree has been completed. With Storm, you have what's called a message timeout defined for every topology. The idea is that if a tuple tree is not completed within that timeout, then it's considered failed and it'll be replayed. And that message timeout defaults to 30 seconds and is configurable per topology. Now, there's a few things you need to do as a user to take advantage of this message processing guarantee. And it's two things. First, you have to tell it when you create a new edge in that tuple tree. This is called anchoring. So here's an implementation of the split sentence vault in Java. And you can see here that when we emit every word for the sentence, we anchor it to that original sentence tuple. That just creates an edge. And then when you're done with the tuple, you have to mark it as complete. And you do that by calling act on the alpha selector. And that's all you have to do, and then Storm will take care of the rest of guaranteeing data processing. So you might think, well, you might wonder, like, okay, how does Storm do this? Right? It seems pretty expensive if you have to actually track the actual tuple tree and like all the pending messages for every spout tuple. Right? Like, what happens if a spout tuple has a million messages pending? Right? That's going to use a lot of memory. Well, it turns out Storm doesn't have to do this, and this is one of the keys to how Storm works, and was really the major breakthrough that enabled me to write Storm in the first place. So Storm actually only uses a constant amount of space for every spout tuple, regardless of how big the tuple tree gets. It's a really cool algorithm. It's all documented on Storm's wiki, and it's ultra efficient, both in terms of memory and computation. All right, so one last thing I want to talk about, which is actually something new in Storm. It's called transactional topologies. So you might wonder, okay, so Storm gives you an at least once delivery guarantee. Well, how do you do something like counting with an at least once delivery guarantee? Aren't you going to overcount? Right? How do you prevent overcounting? The Storm's answer to this is transactional topologies. So like how DRPC is a higher level abstraction on top of Storm's primitives of streams, spouts, and vaults, transactional topologies are also a higher level abstraction on top of the primitives of streams, spouts, and vaults. So the processing model of transactional topologies is a little bit different. So the idea is that rather than process one tuple at a time, you process small batches of tuples at a time, like 100 or 1,000 or something relatively small. And then your topology processes that batch. And if a batch ever fails, if anything in the batch fails, you replay the whole batch from scratch.